Hi, class. It's Mr. Maltzby. As y'all heard the great news, we have no school tomorrow, which means we get to have class online. And if you were wondering, am I serious? I was 100% serious about that. Thank you so much for checking out the video. My guess is this will be the only class we have to do at home, and we'll be back on Tuesday. But if not, kind of Monday night-ish, I'll put up Tuesday's class. And I really appreciate y'all being willing to stay on schedule. It will make a big difference, and I also feel really confident that the stuff that you kind of go over on your own and check out the video ends up being a good educational experience. And I don't really think we're going to fall behind. I think we're going to get off to a great start this unit. We are going to go through the agenda. By the way, this is the only reason I have my webcam turned on, so I can do this. We're going to talk about the agenda and what we're going to learn. And then we're going to start learning it. Make sure you have the packet that I printed out, especially just the Monday pages. All we're going to do is go over the Monday pages. And honestly, I'm going to assume that there's a lot of you that haven't even started the Monday pages yet, and you're just clicking the video, and that's fine. But if you've already worked through them, you've already read through them, I mean, I don't care. If you've already read Tuesdays, that's fine too. You'll just be kind of checking your work or getting more clarification for things you've probably been picking up at least a little bit. All right, I'm going to turn off the webcam now that I got to do my special effects. And we will get started in class. And y'all will have to just apologize for the motion sickness as I click around on my computer. But let's look at our agenda for class on Monday, December the 10th. First thing on the agenda, we're going to read the agenda. That's happening now. And really, here's what we're going to do in today's class. I'm going to go through highlights of the Monday's assignment. So I'm just going to read over a few key sections and mention a few key things without putting up the answer key. I would strongly encourage that it's not that you need to necessarily pause and work out the entire video, but if the video is going faster than even you can read the instructions as the video goes, you do want to hit pause and at least kind of make sure you're reading the problems as quickly as we're working through them. You don't want to fall behind what's happening. We are going to actually go through every answer to Monday's assignment. Some of the answers are incredibly easy, especially the first page. We're going to talk a little bit more about page 4, part 3, which is kind of the point of the assignment or kind of the new idea that's specific to our course. And we're going to at least attempt to preview the first few days of integral calculus. We'll see how that goes. And then lastly, assuming we come back Tuesday, I will tell you exactly what is going to be on Tuesday's pop quiz. It'll be the kind of big picture theme of what we do today. All right, and then we have our learning goals here. These are really simple. I can take the distance of an object. I can find the distance an object travels given average speed and total time. I can graph speed over time. I can relate distance to the area of a speed graph, and I would say this is maybe the calculus component of today's class. I can pay attention to what's on the pop quiz so that I get an easy A. Yeah, I will definitely mention what's on the pop quiz, and it should be easy, but it also should be a nice way of summarizing the video. And I can articulate the difference between the basic concept of differential calculus and integral calculus. All right, so let's go through it. We are just going to go back and do some highlights of Monday's assignment without the answers. And specifically, here's how this is going to go. I'm actually going to read the first paragraph because I don't want you to skip over it. This winter, we're going to shift from differential calculus to a topic called integral calculus. And the journey through the topic will have a similar rhythm when compared to the work from the fall. So revisit the past in order to get a feel for what lies ahead. In other words, we built up a subject from a very basic starting premise, and we're going to build up integral calculus in a very similar way. We're going to ask a lot of similar questions. The very first question in calculus you were asked was, if the beach is 156 miles from DSA and you travel there in 2 hours and 35 minutes, what was your average speed? It was a calculus question that nobody needed help with. Everybody knew what to do. It required a common sense operation. All you had to do was divide. So if you want, go ahead and put divide right here. We incorporated some vocabulary that represents the answer. So in other words, when we talked about divide, we then talked about things like slope and rate of change. And then we separated from our previous understanding by comparing kind of what I would say, like everything before calculus is all average rate of change. And then calculus is how do you find instantaneous rate of change? Because obviously instantaneous rate of change is the more realistic portrayal of what happens in the real world. Nothing in the real world is actually a perfect straight line. Things are always changing. They're changing every instant. And so the ability to do instantaneous allowed us to use slope kind of for practical purposes. All right. I am not going to read over this next little bit. The quick summary is we don't have to learn all of integral calculus today. We just have to get a basic idea of what it's going to be about. Okay. So on the next page, I'm going to put up the answers to these questions as well as those blanks to fill in. These are all really simple word problems. If you haven't read through them yet, you should really pause the video and answer them. It should only take you about 2 minutes. And this is the part where I give you a chance to pause. Some of you are actually pausing right now because you realize that, this is for your educational benefit. Some of you are not. This is my final warning. All right, moving on. So, hey, look, just on this page, I'm putting in those blanks. Division, rate of change, slope, average versus instantaneous. That was kind of the initial conversation we had when we did differential calculus. The answers to the warm-up on the front are pretty simple. If you're on a modern electric train that's traveling 110 miles per hour, how far have you traveled in 7 hours? You take 110 miles over hours, you multiply by 7 hours, and you get 770 miles. I did not expect you to put units in the way I did. I only added that because I wanted to remind y'all of something from the first day of derivatives. That if you know the units for your answer and the units for your ingredients, like the math that makes the units work is going to be the same as the math that makes your answer work. So if you're given miles per hour and hours and your goal is to get to miles, you want to think, hey, what mathematics would allow us to eliminate hours and isolate miles? And it's multiplication. And I know that's overthinking question 1, but I think it's worth pointing out. Question 2, you're now on board an old school coal train, right? So it's going to go at different speeds based on how quickly we're shoveling coal into the engine. Bob shovels coal for 3 hours, causing the train to move 70 miles per hour. So 70 miles per hour times 3 hours, the hours cancel. Engineer Stacy, which is a shout out to Miss Elliott, my favorite of all the math teachers. Engineer Stacy takes over for the next 4 hours, 100 miles per hour, 4 hours. That's how far Stacy's going to get the train to move. And then last one is Engineer Hector. Only has to shovel for an hour, so he can really get it done for that hour. 1 hour, 120 miles per hour, 120 times 1. And you add up all three of these values, and you get 730 miles. And this was basic stuff. If we had school for real, none of y'all would have asked for help for the first 2 questions. Sometimes students ask for help for question 3, but that's only because the instructions are confusing. So soccer coach Green has a new warm-up run. Every 10 seconds, our athletes must increase their speed by 1 foot per second. How far have they traveled in 60 seconds if they started out running 5 feet per second? So in other words, they got to run 5 feet per second for 10 seconds. And then after 10 seconds, they have to speed up a little bit. Then for the next 10 seconds, they run 6 feet per second. Don't know what's up with that T. Then they run, for 10 seconds, they run 7 feet per second. So there's 2 ways to work this out. And if you're somebody that did the assignment on your own, I guarantee this is what you did. You said, okay, I'm going to run 5 feet per second for 10 seconds, plus I'm going to run 6 feet per second for 10 seconds, 7 feet per second for 10 seconds, 8 for 10, 9 for 10, 10 for 10. Now, I'm not necessarily saying you wrote it all out as one line, but you just thought of it as 5 times 10, 6 times 10, 7 times 10, and came up with a total. And that's great. That's the common sense way to do it. I want to point something out that's going to pay off later if we recognize it. Every one of these terms has a common factor of 10. So just mathematically, it would be legitimate to factor out 10 from every term. And what you're left with is 5 plus 6 plus 7 plus 8 plus 9 plus 10. And that's just another way to get to 450 feet. So I would not expect anyone to do it like row 2, but just recognize that row 2 is mathematically legitimate because we're taking row 1 and just factoring out 10. And that's something that'll kind of matter more later as we get into the kind of full-fledged integral calculus stuff. All right. Hey, for the next couple of problems, what I asked you to do is make a graph where the horizontal axis should be time and the vertical axis should be rate of change. So in other words, we're going to put miles per hour here. We are not going to put miles. If we put miles, we would have a linear graph. At 0 hours, you've gone 0 miles. And the graph would increase because as time goes by, the miles goes up. But that's not true. Our y-axis or our vertical axis is going to be the rate of change. It's going to be miles per hour. So if you're not doing horizontal lines, you're doing it wrong. And we're going to do that for each scenario. For the electric train, we're going to graph the miles per hour over hours. For the coal train, we're going to graph the miles per hour over hours. And remember, we had 3 different miles per hour because there were 3 different engineers shoveling the coal. And we're going to do the same thing for Coach Green. And this is just how it's going to look. All right. 110 is the constant speed, so we're going to graph a constant function. And our units over here are miles per hour. If they were miles, this graph would look a lot different, but they're miles per hour. And then this is just our hours. We're going to do the same thing for the coal train. So that first horizontal line, that's, I think that was Bob, 3 hours, 70 miles per hour. Engineer Stacy, 4 hours. Remember, Stacy takes over at the 3-hour mark. So this is kind of like a piecewise function. And then for the last hour, so from t equals 7 to t equals 8, Hector is 120 miles per hour. And then Coach Green. Coach Green is going to be a little different. Coach Green is going to look like this, right? So for the first 10 seconds, that's your speed. For the next 10 seconds, that's your speed. And so on and so forth. All right. I meant to focus on this question. I do want you to take a moment and think about the following. On the graphs we've made, the answers to page 1 can be found on the graphs. For an example, the answer to the first question was 770. Something about the graph we made is 770. Oh, by the way, if I was you, I would stop and draw those graphs. If I was going too fast, go back to the first graph, draw that horizontal line that's 110 on the y-axis. Or for graph 3 and graph 2, draw those horizontal lines piecewise. And just so you know, on those graphs you made, the answers on the first page measure something on those graphs. And kind of recognizing that there's a measurement not yet discussed. So in other words, something about this graph, it has a measurement of 450. It's not the y, because the y's are 5, 6, 7, 8, 9, 10. It's not the x, because the x's are 10, 20, 30, 40, 50, 60, or it's not the time. But there is a measurement on here that's 450. And it's not the slope, because the slopes of all these are 0, which is a coincidence. That's not always going to be true. So what is 450 on this graph? Or what is 770 on the first graph? And then the answer is the value of each answer is equal to the sum of the area of the rectangles bounded between the t-axis and the function. This sentence right here is actually one of the 2 things that's going to be on the pop quiz. I'm just going to straight up ask you, I'm going to give you a graph, and I'm going to just say, how is the answer, and it'll be like miles, related to this graph? And the answer will be the sum of the area of the rectangles bounded between the t-axis and the function. Now, we're going to pause and talk about what that means. So you may be asking, what rectangles bounded between the t-axis and the function is he referring to? I'm a little bit lost. So let's jump over and look at some rectangles. I've gone back and taken that first graph, and I have just added a big pink rectangle. The rectangle is between the function we graphed and the t-axis. So that's what it means to be bounded, right? This is the upper boundary of the rectangle. This is the lower boundary of the rectangle. And this rectangle has an area, right? The area of a rectangle is the base times the height. Well, if we look, the base of the rectangle is 70. The height of the rectangle is 110. So base times height is 770. And if we think about units, base is hours, height is miles per hour. So base times height is hours times miles per hour. Base times height is going to be miles. And what we're going to do is just scroll through and kind of look at the rectangles of every graph. Right. This graph has 3 rectangles because there were 3 horizontal lines. So our first rectangle, base is 3, height is 70. 3 times 70 is 210. That is the distance engineer Bob got the train to move. Or our second rectangle is 4 times 100. It's 400 miles. So that is the distance Stacy got the train to move. And lastly, our last rectangle is skinnier. It has a width of 1. It has a height of 120. Or it has a base of 1 and a height of 120. 1 times 120 is 120. Add up all 3 rectangles, and the total sum of these rectangles is going to be equal to that distance the train traveled. So that's one of our learning goals for today, is just to recognize that the distance on a speed graph represents the I misspoke. Let's be correct, right? We can relate the distance to the area of the speed graph. The area on the speed graph that's between the function and the axis is going to be the same as the distance the object travels. And that's going to be true no matter the shape of that graph. Just whatever area is under your function, it's going to be hours times miles per hour. So it's going to be miles. And then lastly, Coach Green. Right, so Coach Green had 6 horizontal lines, so we can make 6 rectangles. Each rectangle has an area, 10 times 5, 10 times 6, 10 times 7. So they all had constant width of 10, and they all had different heights. So they had different areas. If you add up all these areas, you get 450. You get the total feet the soccer players are going to run. Okay. So let's jump down and do the homework. This is going to be pretty simple. The homework, no matter what, the velocity of a squirrel is shown in the graph below. The units for the y values are feet per second, and the units for the x values are seconds. How far has the squirrel traveled? Well, these are not necessarily rectangles under the function, but that doesn't affect what the units are. Much like in the last half of the class, in derivatives, we said, oh, your slope is always your y divided by your x. Well, your area units are always your y times your x. It doesn't really matter if this is a bunch of rectangles, a bunch of trapezoids. Honestly, it doesn't really matter if the graph was just some kind of non-linear curving object. If you wanted to work out the area under that graph down here, the units for that area are going to be feet. They're going to be feet per second times seconds. The shape of the area doesn't affect what the units are. So if we want to figure out the total feet the squirrel traveled, we want to figure out the area under the graph. And what I did here was I just broke it down into some easy to evaluate sections. These two triangles have an area of 10 and the units are feet because it's always base times height. Area is always base times height. That is just always true. Those formulas like 1/2 base times height, they always introduce a coefficient, but base times height is always the variables for an area formula. Always. Even pi r squared is actually base times height. The base is r, the height is r, and it's not quite that simple, but area is always base units times height units. That's always true. So this is going to be feet. This is going to be 120 feet. Okay. We're actually now done with the assignment. Honestly, if you just recognize that the answers on page 1 kind of line up with the area of those rectangles, you're good to go. What we're going to do here is look at one last thought for future learning, and then we will I'll tell you what else is going to be on the pop quiz. So remember, there's going to be 2 questions on the pop quiz. This is going to be kind of a question, or you're going to be tested on this concept that the distance from the distance an object moves is the same as the area on a graph of the speed, right? Connecting the graphs we made to the warm-up questions. That's going to be half the pop quiz. And I'll tell you the other half in a minute. I just want to pull up a question for future learning. And you'll have to give me 1 second. So we're going to look at the Coach Green problem. And I need to do a little bit of adjusting. And for the moment, don't really worry about that. Okay. The question on page 1 was very easy to come up with an answer. It's easy for Coach Green to tell her athletes to run 5 feet per second and then run 6 feet per second and then run 7 feet per second. It's an easy scenario to imagine. But is it an easy scenario to actually do? Do you think a human being can run exactly 5 feet per second and then instantly speed up to exactly 6 feet per second and then instantly speed up to exactly 7 feet per second? In other words, can a human being actually achieve the graph that we made? And I think the answer is no, right? You would, whether it was linear or nonlinear or whatever, you would kind of have to speed up from 5 to 6, from 6 to 7. So while this is certainly an easy graph to make, and it's very colorful, and it's an easy value to work out, it's not actually very realistic. No human being could actually just jump from speed to speed to speed at exact 10-second intervals. A human being would more likely have a function that looked like this, where they start off at 5 feet per second. Maybe they end up at 10 feet per second. But over the course of those 60 seconds, we'll say each one of these counts as 10 seconds since it's 0 to 6. Over the course of those 60 seconds, they would gradually speed up. So when we worked out that 450, what we didn't really work out was the actual distance the soccer players ran. We worked out an approximation. If you look at all these, if you think of this as like shading, if you think of this as like just kind of gray shading, this has an area. And if the units are feet per second and seconds, the units of this area are feet. The actual area of this shaded region is the actual distance the runners run. What we are going to explore is, well, working out the area of something non-linear and non-geometric is kind of complicated. Let's approximate that area by filling it up with rectangles. So rectangles are easy to do. Base times height, add them up. But we're not going to use them to calculate exact values. We're going to use them to calculate approximations, because no scenario would truly be a bunch of linear constant graphs. It would be something non-linear. So if we wanted to take this approach, we wouldn't be getting an exact value. We'd instead be getting an approximation. And so we would say, oh, they've run approximately 450 feet based on our thing. And I don't think I did the best explanation for that, and I'm not worried about it because it's what we're going to learn in the future anyway. And we'll probably cover it better when it's the right time. Okay, hey, last thing that's on the pop quiz. The value of each answer is equal to the sum of the area of the rectangles bounded between the t-axis and the function. I don't think memorizing that sentence is a good idea. I think understanding the video is a good idea. Hey, if we work out the area, we work out the distance. And then the other part of the pop quiz is a summary of what our unit's going to be about. And this is kind of an official phrase, okay? We used to be in the division business. In the fall of 2018, we were in the division business. In the winter, we are going to be in the multiply business. We're out of the division business. Now we're in the multiply business. We used to be in the slope business. If you thought we were going to talk about slope all year long, you're wrong. We're actually out of the slope business. We're no longer looking at graphs and asking the question, what's the slope? Now we're in the area business. We used to be in the rate of change business, right? Because if we're in the slope business, we're talking about rate of change. Well, when you measure area, you don't measure rate of change. You measure what we're going to call total change, right? The total change in miles the train traveled. That's not a rate of change. That's an amount. So we're in the amount business. We used to be in the derivative or differentiation business. Hey, guess what? When you're in the multiply business, when you're in the area business, when you're in the total change business, you're no longer in the derivatives business. Now you're in the integration business, or you're in the business of working out integral values. All right. Hey, that's the video. I really appreciate it. I hope that we're in class on Tuesday, just because I think there's a lot of good stuff that we want to discuss in person. If we don't have school Tuesday, on Monday night, I'll put up another video. I really, really appreciate it. I hope y'all learned something today. All right. Love you. Bye.